Okay, we're going to do some demos to illustrate the second and the third laws of thermodynamics. So, as we did last week, there is not a lab from your publisher over these topics, which I find ridiculous, but that's okay. We get to play. We can just play a little bit and have some fun. So, if you would, in your journals, we're going to be like having you engage what we're doing here. Somebody help out your fellow, I almost said siblings. We're kind of all brothers and sisters, but only in the Lord, not really in biology. Somebody help out your fellow students and tell us what is the second law of thermodynamics. And I can't even say that without that old song coming into my head. The second law of thermodynamics.
Energy flows from areas of higher energy to areas of lower.
Energy always flows from areas of higher energy to areas of lower energy. That cool song that was in your menu that you could have listened to, heat always flows to the cooler from the hotter. You can try to make it backwards, but you'd really better not. It's great. Anyway, heat always goes from areas of higher concentration to areas of lower concentration. So I have here in front of me a beaker of water and a Bunsen burner. And somebody talked to me about the ways that heat is flowing. The ways in which heat is flowing. I think I said that right. Yes. Oh yeah. Or you could move your person, but yeah, that'll work. So where is heat flowing? From where to where?
From the fire to the coal.
From the fire to the beaker. That's almost totally true. It goes somewhere in between there.
Oh, the melting.
Yeah, so we're heating up this mesh, and then the mesh gets hot, and then the mesh transfers some thermal energy. Where does it go after that?
In the air.
Into the air?
And in it.
Oh yeah, but where does it go between the mesh? Where else is there thermal energy flowing?
Glass.
The beaker, the glass, yeah? And the glass gets really hot, and then where does the glass transfer its thermal energy?
The water.
And what does the water do with thermal energy?
Evaporation.
Right, yeah. And does anybody remember for 200 bonus points? The word that has to do with energy that does not actually change the temperature of something, but rather changes its state? No, that would be a solid going straight to
Condensation.
These are all phase change words. We're looking for the name.
What does it start with?
It starts with wool and ends with agents.
Latent.
Oh yeah, good job. This is the latent heat of evaporation, and what we're doing here is we're taking water molecules that are close to each other, and we are adding thermal energy to it, which makes them vibrate more violently, which drives them apart from each other. And as it boils, we're doing work, right? With this heat, we're separating the molecules, and water molecules that get separated far enough from each other stop being liquid and start being gas, and this is what's happening here. So we have heat transfer. Now, there are a couple of different ways that heat can be transferred. Heat can be transferred 3 different ways. What are the 3 different ways that heat can be transferred? Con, and earth. I know, I'm making you remember back to chemistry. Convection is one of them. Convection is the transfer of thermal energy through a fluid that causes the fluid to stir. So you'll notice that the liquid is stirring as it is boiling. And also, if you had really cool infrared vision, you could see that the air above the beaker and above this whole system is also stirring, and that's also convection. So convection is one. 2 others. Conduction, ding, ding, ding. Conduction is direct heat transfer or thermal energy transfer because objects are in contact. Where here do I have objects in contact and heat is transferring?
The mesh and the beaker.
The mesh and the beaker, very good. Heat is, thermal energy is transferring because they're in direct contact, and then radiation is the third, and that in the perfect definition would be thermal energy or energy transfer across a vacuum. We don't really have that going on here because we're not in a vacuum because I don't want us to be dead. But but I can feel the heat from this, and the thermal energy that's leaving this system and striking the palms of my hands. I can feel heat, and I'm not obviously touching this because I'm not stupid, and I'm not boiling. This is just radiation. Okay, so heat flows from a higher concentration to a lower concentration. We talked about that there are heat insulators and heat conductors. The cool thing about that, we all look at this and we're like, of course it's boiling water in a beaker. That's what you do with beakers, you boil water in it. And nobody's brain is like bugged out by that because this is a normal setup. But if I were to just take, I'm going to take this, starting to boil more rapidly. I'm going to take this beaker away and hopefully not get, matter of fact, I'm going to turn that off, not get burned when I do this. But I'm going to take this beaker away, I'm going to set it aside, and I'm going to replace it with a paper cup. Now, paper, anybody know the temperature at which paper boils?
20. I mean,
20. Because paper burns at 20 degrees?
No.
Oh my goodness, your paper plate is a miracle because it's warmer than 20 degrees. Anybody know? Anybody know temperature at which paper burns?
100.
It's more than that. If you walk outside on a 100-degree day, your textbooks do not burst into flames. It's hotter than that too.
300.
So in Fahrenheit,
400. 500.
451 degrees Fahrenheit. Celsius, that's going to be, I don't know, 200 and something Celsius. So what temperature does water boil? If paper burns at about 200-ish Celsius,
800.
water boils at what temperature? Celsius. Water boils at 100 degrees Celsius. Thank you. Yes, that's how we set the Celsius scale. So will the water boil first or will the paper burn first?
Paper burn first. No.
You think that, right? Because you're like, he better not light that paper cup on fire.
Because Celsius is like half of Fahrenheit.
Yeah.
So then therefore, if it boils at 100 degrees Celsius, then it should like
Right, so the water will boil at 100 degrees Celsius, the paper will burn at about 200 degrees Celsius, which means that if I apply heat to this cup, and if the cup is a good second law of thermodynamics obeying device, it will give its heat away to the water. And the water will absorb a whole lot of heat, and then eventually the water will boil, and then the paper cup will not get any hotter than 100 degrees Celsius because the water doesn't change temperature while it's boiling. So I'm going to blow your mind. Here I have a paper cup over a fire. Now, there is a part of the paper cup, this bottom little rim, where there's no water, right? The paper cup has a little lip on the bottom. That may char. But the cup itself is going to be just fine. And I will be able, if I were to have the patience, I would be able to boil this water in this paper cup. And you could like make yourself a cup of coffee with a paper cup over a campfire. And that is just really, really strange because you would expect that the cup is going to catch on fire. But the cup's going to give its heat away to the water because heat flows from areas of high concentration to areas of low concentration. And the water is going to be able to absorb a bunch of this heat. This is really cool. Now, would the paper cup survive being over a Bunsen burner like this if there weren't water in it?
No.
Why? Right? A little spiritual application. The bottom of the cup is going to char. Matter of fact, we should probably have a fan underneath that fire extinguisher, or fire smoke detector. Just a second. The bottom of the cup will char, but it will not burn. Let me pause this. Okay, so as I was saying, spiritual application. Pretend the cup is you. Pretend the fire is all the stress of being a senior and trying to take economics and trying to get ready for college and trying to decide what to do with your life, and you've only got 15 more weeks, and then you are launched out of this cannon, and you have to be responsible for your own life. Congratulations, you're a little bit stressed. And the fire is on. The average paper cup is not going to make it. You're going to be like, oh my goodness, all this stress, and you're going to find yourself bursting into flames. But what happens if the Holy Spirit is in your life? He gets to absorb your fire. Isn't that cool? It's not that the fire goes away. Fire's still on this paper cup. But this paper cup is not burning where its friends will, because the Holy Spirit is in you, the water is in this paper cup, and the heat can get transferred to it. The Holy Spirit can take a lot of your stress. The Holy Spirit is never going to look at you and be like, what am I going to do with Noah? Right? Never. So you can transfer your anxiety to Him. You can cast your cares on the Lord, and He will care for you. Pretty cool. Just like the water in this cup is literally saving this cup right now. It is keeping the cup from burning. Isn't that neat? So, second law of thermodynamics, heat flows from areas of higher concentration to lower. The fire is hotter than the metal. The metal is hotter than the cup. The cup is hotter than the water, but right now the water's taken all the abuse, and it can take it. So the heat is transferring into this water, and if I were to leave it there long enough, I'd get the water to boil, but I've got other things to do besides that. But isn't that cool? I think that's pretty cool. We would all be amazed at the paper cup thing. It gets cooler than that, though, because just like we don't normally think about paper cups as being a good thing to boil water in, you probably also wouldn't think of a balloon. What? You're going to boil water in a balloon?
Yeah.
Totally am. So it's going to pop. It's not going to be able to take it. Now, normally, latex and fire are not friends, right? Latex, yeah, fish are friends, not food. Latex and fire are normally not friends. But again, the latex is going to transfer the heat to the water. It's the same exact science. And so we're going to do this. Now I'm going to, if anything's going to go wrong today, it's this. So I'm going to go ahead and move my mouse to the side so I don't break it. But the latex is going to transfer the heat to the water. It's the same exact principle.
Wait.
If anything goes wrong, though, it's this. Oh, look, it just started to go wrong. Okay, so that would have been... It almost worked perfectly. I'm peeing on my floor. Okay, so... Okay, it worked for a little while. It'll work for a little while. Okay, so heat always flows from areas of high concentration to areas of low concentration. We've seen it flow with heat from something that's hot to something that's not quite as hot. Let's go backwards. What's this?
Ice pack.
How does an instant ice pack work?
You have to crush it. You have to apply heat to it.
No, you don't. But I don't like the way you're thinking. How do these work? Do you remember? I know, I'm making me think back to chemistry. We talked about exothermic and endothermic reactions. Ammonia and Epsom salts. The chemical reaction that happens between ammonia and Epsom salts absorbs thermal energy from its environment. So there you go. Hold that. Nice and cold, right? Nice and cold. Nice and cold. Why is that cold? Why is that cold to you? Why do you hold that and go cold?
Absence of heat.
Not absence, but it has more or less thermal energy than your hand. So thermal energy always flows from areas of higher concentration to areas of lower concentration, right? So that means here. That means that where is thermal energy going right now?
To the ice.
To the ice pack from your hand, right? So we talk about how something is cold, right? And you shake the stuff together and it makes cold or it gets cold. Cold is not a thing. Cold is we should say rather that it's a heat sink. It is something that has far less thermal energy than its environment. Here you go. And so when thermal energy is around it, the thermal energy... Do you want this? Now I'm holding this cold, wet thing. Thank you very much. Thermal energy from the environment is going towards it because thermal energy always flows from an area of higher concentration to an area of lower concentration. No, I don't think you got to hold the cold thing. Congratulations. So that is that is the second law of thermodynamics with regard to thermal energy. Take a moment and summarize some of the things that you just saw and why that describes the second law. Okay, so the other aspect of the second law has to do with entropy. Somebody tell me, what does the word entropy mean?
Wait, it is the measure of disorder in a system.
The measure of disorder in a system. That's not loud and annoying at all. Hold on, let me see if I can fix it. Okay, so entropy is a measure of the disorder in a system. Does the second law of thermodynamics say that entropy in a spontaneous situation will increase, or entropy will decrease? Entropy will increase. The amount of disorder or chaos in a system goes up in a spontaneous natural activity. Here I have a deck of cards. Jaylee, would you come on up here and be my lovely assistant? Could you tell me, Jaylee, is there an order to these cards? Just look through them. Is there an order?
No.
Wait, think more carefully.
Yes.
Yeah. What could you tell the class, just summarize what kind of order are those in? Numerical order, and they're by suits, right? 2?
Oh, this one's wrong.
2. Oh, thank you. See, she's increasing the order. She's decreasing the entropy. Okay, there you go. So it's in suit order and it's in number order as you go. Very cool. Jaylee, if you were to do something to the order of those cards, shuffle them, deal them, ruffle them, slide them across on the table, would the amount of order in that system go up or go down? The amount of order in that system would go down, right? So chaos would go up, right? Cool. Would you do me a favor? Would you just toss that whole deck in the air? Make a pile? Yeah, totally. Throw it in the air.
Oh,
Okay.
so labor
Now, would everybody help and pick these cards up? Come on, help me. Pick these cards up. Pick these cards up. Wait, this didn't quite get scattered as much as I wanted it to. Okay, pick these cards up. Help me. Just put them in whatever order that you pick them up. Okay? Pick these cards up. There you go. There you go. And as we bring all the parts of this deck back together here, we're gonna just here, can I have your cards? And notice that even as we've brought it back, because we're creatures that enjoy order, we've put them all face up and we put them all like together in a nice, neat little thing here. Oh, here's one more. Is now, Andrea, come on up. Are these cards still in number and suit order?
No, they are not.
No, they are not. Because we have just had a spontaneous event. And the spontaneous event increased the amount of disorder, thank you, in a system, right? And that's the way that every natural event will work. It's not that you can't organize things. I organized the deck of cards before the demo. Organization is possible, but organization takes intention, takes some unusual circumstances like a 40-year-old dude organizing cards, right? But a natural event, like throwing them up in the air, is never going to increase order. It will always increase chaos. Spiritual application, there is really 2 views for how the universe came to be. One of them is that an ordered, intelligent, powerful being created the order by speaking it into existence. We call that creation. Another category of creation possibility is that nothing had a random spontaneous event, and out of nothing, randomness created order. It's called the Big Bang. Which of those goes with the second law of thermodynamics, the first one or the second one?
Second.
The first one, yeah, thank you very much. I was about to quit my job as a Christian school teacher. The first one agrees with the second law of thermodynamics, that in order to increase order, you have to have some kind of strange circumstance where things conspire in a very particular way to bring about order, like me organizing cards. But random natural events never do that, right? Okay, cool. Another example. Here I have a soda bottle, and in case people are going to watch this on YouTube later, this is not a beer bottle. I know it's brown and it has a label, but it says C-Pop. C-Pop. Okay. Soda. And this soda bottle is organized. Would you agree this is organized? What are some of the ways that this is organized?
It's yellow, yeah, it's not broken. It's no label.
The label's on it, nice and neat. It is in a uniform sort of shape, right? There's symmetry to this. It has radial symmetry. Wherever I go like this, it's going to be essentially the same thing. If I were to look at this under a microscope, I would find that there are silicon molecules, silicon ions arranged in a lattice work with some other things to make it brown, and it's a very regular, mostly crystalline sort of pattern. I have to be careful because glass is technically a supercooled solid. I mean, supercooled liquid, but mostly crystalline solid thing. So if I have a random event occur to this, am I going to increase or decrease the amount of order? I'm going to decrease the amount of order. Okay, that went down my shirt. Caution, glass goes down shirts. So, oh, thank you for that. So, everybody's watching on the internet going, he didn't wear protective eyewear. I have glasses on. So, I just decreased the amount of order and increased the amount of chaos. Now, here's the cool thing. Sometimes events that increase chaos and decrease order can be reversed. But most of the time, they cannot. The huge majority of the time, events that increase chaos are irreversible. Is this a reversible event?
No, yeah, unless you take out, unless you blow the acid.
Right, like I could throw the whole thing in a furnace, I could melt it down, and I could re-blow the bottle, and I could somehow recycle the paper, and I could reprint a new label. I suppose it is technically reversible, but it would take a whole lot of energy and a whole lot of work. Most of the time, events that increase chaos and decrease order are irreversible. Okay, this ice pack, you held it right after I popped it. Is it just as cold as it used to be? Or is it a little bit warmer? It's a little bit warmer than when I first did it. I'm finding little shards of glass. Should have used maybe a better glass example. But the reason this is not still entirely as cold as it used to be, well, maybe somebody else should tell me that. Why is it not quite as cold as that used to be? What has it been doing? And doing what? We talked about that. Thermal energy has been flowing from the environment to where? To it. So it's not as cold to the touch as it used to be because some thermal energy has gone in here. Now, this is a chemical reaction. The amount of chaos increased in this chemical reaction. Is this a reversible chemical reaction? No. This is an irreversible chemical reaction. You could never get this back. Some chemical reactions are reversible. This one happens not to be. So I can't recycle this cold pack. I just wasted the cold pack on the science demo, but it's okay. The school will go on. So this was an irreversible chemical reaction. Another example of that, if I take, I'm going to get my burner back. If I put some sugar in this tinfoil cup, hey Noah, something tells me that when sugar burns, there's smoke. Somebody did a science fair project related to that in some way. I think that sounds somewhat familiar. I'm going to use a little bit less sugar because I want to make a little bit less smoke. But if I get the sugar nice and hot, the sugar is going to get nice and hot, and in a moment, it will start to burn. And when it does, I'm going to carry it over closer to the window so the smoke goes out. There we go. Starting to get brown. I'm going to help it out because I don't have a bunch of time. I'm not helping it out all that much. There you go. There you go. There you go. There it goes. Okay. So the sugar is now burning. Smoke is forming. Is this chemical reaction increasing or decreasing the amount of chaos in the system? Increasing the amount of chaos in the system. I've got a crystal here that's pretty ordered, and then I get this chemical reaction going, and I get smoke, which is totally chaotic and going all over the place. So this chemical reaction increased chaos. It obeyed the second law of thermodynamics. Is it reversible? Can I take that black char and like put it on my cereal? No. It can go backwards, but it would take a whole lot of work and other things, a whole bunch of energy going into it to make it go backwards. So irreversible. Second law of thermodynamics also has to do with an increase in chaos and things not really very often being able to go back to the way they were. Take a moment in your journal and describe how we just demonstrated. Okay, last thing I want to do is do some demos of the third law of thermodynamics. The third law of thermodynamics is not actually all that much fun, and there's not a whole lot that you can do to demonstrate it, but we will try. So what is the third law of thermodynamics? Somebody? Absolute zero is impossible. Because absolute zero would be the condition where there is absolutely no thermal energy. Now, you would think that that would be attainable, that we should be able to get something cold enough that it has no thermal energy. And when that was first written out, that when it was discovered what absolute zero was, it seemed intuitively like we should be able to achieve it. Scientists in very strange controlled circumstances have gotten really close to absolute zero. Within a few, I read in one article, within a few billionths of a degree. So, I mean, honestly, when it comes to what temperature is it, very few of our thermometers measure to billionths of a degree. But it's still not truly absolute zero. And the idea is, when I'm holding this cold pack, it is cold, and it feels cold to me because thermal energy from my body is going to it, and it is absorbing thermal energy in my body. And I put it on a sore part of me, and it feels better because the thermal energy from the inflammation goes into it. It cools this part of me because it absorbs thermal energy. A refrigerator works because it gives the thermal energy somewhere else to go. It takes the thermal energy from your cucumbers, and it puts that thermal energy into Freon, and then it dumps that thermal energy out into your room. So the colder your cucumber is, the hotter your kitchen is. Okay? The heat gets pumped out of your food and into your kitchen. And so the idea there is that the thermal energy has to have somewhere to go. In order for something to be cold, it has to have put its heat somewhere else. So if we are getting the world's best freezer together, it has to be able to put its heat somewhere else, and that something else has to be colder than it was. The Freon in your freezer, your refrigerator, is colder than the cucumber in your refrigerator. That's why the thermal energy from your cucumber went into the Freon, because the Freon was colder than it. Okay? So in order for you to get a freezer that would get down to absolute zero, you would have to have some kind of refrigerant to pull the heat energy out of the absolute zero freezer, which would require that there be something colder than absolute zero to put the heat, the thermal energy in from your absolute zero freezer. So it's a little bit confusing. Imagine that thermal energy always runs downhill. It always goes from an area of higher concentration to lower concentration. Thermal energy in some item is here, and it gets colder as we dump its thermal energy from it to something that is already colder, then it gets to get colder. Now, in order for this thing to get colder, we've got to pour its thermal energy into something that is already colder in order for it to get colder. This thing, if we want to get this to absolute zero, we would have to pour its thermal energy into something that is colder than it. Is there anything colder than absolute zero? No. So while you can get stuff really close to absolute zero, in order to get it to absolute zero, you would have had to have taken the last few microjoules of thermal energy out of it and put it somewhere else, and that somewhere else would have had to have already been colder. And so because there is no heat sink that can sink enough heat to get something to absolute zero, we'll never get there. Interstellar space, if you take the temperature of space that is equidistant from lots of stars long, long, long ways away, and it is getting very little thermal energy from any kind of star nearby, interstellar space is about 2 degrees Kelvin. So it's stinking cold. But 2 degrees Kelvin is still not absolute zero. We've gotten colder than interstellar space in labs, but you can't get all the way down. Okay, so I can't really demonstrate that for you because I can't say, look, this isn't absolute zero. That's not very exciting. Nothing is absolute zero. But just know that just like this feels cold because thermal energy is flowing to it out of me, same idea, we'd have to have something where the thermal energy flowed out of the absolute zero freezer, and we can't. There's nothing for it to flow into. Okay? So, second and third laws of thermodynamics. You should have some notes in your journal about things that I demonstrated for you today. Are there any questions?